We propose an adaptive robotics framework that aims to perform chemistry experiments. The proposed framework facilitates material discovery by using robots to help chemists through automating laborious experiments that might be dangerous. We verified the utility of our framework with several chemistry experiments, including solubility and recrystallization. The framework is composed of three main components: perception, task and motion planning, and skills. For input, the framework receives chemistry experiment instructions through a standard description language from a chemist and also perceives the workspace. Afterwards, it generates task and motion plans with considerations for handling vessels with chemical reagents, allowing the robot to perform chemistry experiments autonomously. The proposed framework can adapt to new workspace configurations in a semi-structured environment. It can scale by embedding new perception and skill algorithms, as well as integrating new hardware with a ROS interface. We use PDDL Stream to do integrated task and motion planning. PDDL Stream is extended with a custom constrained motion planner to guarantee for safety consideration during liquid manipulation, the importance of which is shown in this video. We evaluate the constrained motion planning performance of a 7 degree of freedom and 8 degree of freedom robot in two scenarios. In the first scenario, shown here, the robots find a constrained path with a fixed orientation from initial to target positions that are randomly sampled. The table shows the first scenario performance of both robot configurations in terms of inverse kinematics and constrained motion plan success rate. The second scenario, shown here, extends the first with an additional intermediate sampled waypoint. The table shows the second scenario performance. With material transfer being an essential skill in a chemistry lab, we implement the pouring skill. Inspired by human motion, we present and analyze a set of accurate and efficient pouring skills for liquids and solids. We realize accurate closed-loop pouring skill by convoluting a PD controller with a shaping function for velocity control. Here we show several pouring skills. On the top row, the robots pour water using a standard beaker. In the center, we show that the robot can pour higher viscosity liquids such as oil. The robot can also pour fine powders and solids such as salt. When compared to the PD control baseline, our method achieves higher precision for both liquids and solids. Solubility measurement was conducted to demonstrate the utility of our framework. The robot motion is generated from the experiment description specified in KDL format by the Task and Motion Plan module. By using constrained motion planning, the robot can carry the beaker without spillage. In this experiment, 10 grams of water is repeatedly added until all salt dissolves. Turbidity value is measured by hand and camera, and the dissolvement of salt is automatically determined by the relative change of turbidity values. We use turbidity of the solution to determine whether the solute has dissolved into the solution. The turbidity decreases as we pour more water and stops changing when all solutes have dissolved. The robot continues pouring water until the difference in the turbidity before and after stirring is smaller than the threshold. Here we show the recrystallization experiment, an experiment fundamental in molecule synthesis. First, it preheats the water on top of the hot plate. Then it grabs the solute and pours it on top of the dish. Later, it pours the hot water into the dish to dissolve the solute. The device stirs and heats the solution. After 1 day, we obtain crystals. Please visit our website for more information. Thank you.